Hello everybody, today we're going to be talking to you about our potable water reuse design project in Moscow, Idaho. We are the University of Idaho Student Design Competition team. I am Kylie Cutler, an undergraduate at the University of Idaho Civil Engineering program.
I'm Lindsay Smoot, and I'm a graduate student at U of I studying civil engineering.
And I'm Nicole Brower. I'm also a graduate student at the University of Idaho in the Civil Engineering Department.
So to give a quick overview of our project, what we initially began with is a literature review of the different technologies commonly used for potable reuse, both in the United States and globally. Looking at these literature reviews and after our research, certain treatment trains began to stick out more than others in effectiveness and common use. We chose 3 of these alternatives to evaluate for our design project. In order to evaluate these alternatives, we wanted to make sure we were choosing the right metrics and what really mattered for real design. So we performed industry consultations where we spoke to experts in the field, as well as the city of Moscow, to see what was most important to them when we were making our decision. So using this decision matrix, we were able to evaluate our 3 alternatives and choose the option that had the best results according to what was preferred by the city of Moscow and professionals. So lastly, we took the successful alternative and we chose the technology that would be implemented at the Moscow plant and created a design and site overview. Next slide. So to give some context to the project, why did we choose to do a project about potable reuse in Moscow, Idaho? It's because Moscow, Idaho, and its neighboring city, Pullman, Washington, both draw all of their water from the Grand Ronde Aquifer. And as you can see from this figure, this aquifer is dropping very quickly at 1 to 2 feet per year. People in the community began to become quite concerned about this in the 70s, and that's when the Palouse Basin Aquifer Committee was created in order to promote water conservation and ensure that future generations would have clean, accessible water. They created the Groundwater Management Plan, which allowed the communities in the area to sign on to a voluntary water usage commitment. And Moscow, Idaho is quickly approaching their production limit that they agreed to within this plan. Moscow has already implemented quite a few different technologies in order to conserve water, with their most successful one being that they treat their water to the point where it can be reused for irrigation. But we believe that Moscow needs to start pursuing more aggressive routes for water conservation, such as potable reuse. Next slide. So Moscow's current water resource recovery facility has the effluent averages shown in this chart, and these are what we used as our design parameters. So this facility currently has preliminary treatment, secondary sedimentation, disinfection, and solids handling. Next. So it's important to note that when we speak of potable reuse, there are many different kinds with 2 main categories. These 2 categories are indirect and direct. So the 2 different types of indirect potable reuse are groundwater recharge and aquifer recharge. And for direct, there's reservoir, raw water, finished water, and finished water augmentation. For our project, we did 2 direct and 1 indirect. Next slide. So unfortunately, in the state of Idaho, there are no regulations when it comes to potable reuse, as it's not a common occurrence. But California and Washington are a little bit more ahead of the game, since water is a bit more of a concern in those states. Because they're neighbors to Idaho, we decided to choose them and use their regulations to guide our design decisions. These regulations include having 3 or more technologies, a 12 log removal of viruses, a 10 log removal of crypto and giardia, and finally less than 10 milligrams per liter of total nitrogen. Next slide.
We considered 3 alternatives for this design project, 2 of which are that finished water augmentation DPR, and a third is aquifer recharge indirect potable reuse. The first direct alternative is ultrafiltration, reverse osmosis, and UV AOP. The second direct alternative is ultrafiltration, pre-ozonation, BAC, and post-ozonation. And the third indirect alternative is ultrafiltration, reverse osmosis, chlorine disinfection, and deep well injection. We used a decision matrix to make our final design recommendation. The matrix was composed of 4 main metrics, each with sub-metrics, with exception of the first metric, which was treatment. This metric just considered if the alternative was able to meet the regulations previously discussed. The second metric is effectiveness, which is composed of regulatory approval, public acceptance, and future flexibility. So with this metric, we tried to consider if the alternative not only was effective presently, but in the future. The third metric was cost. We broke it down into capital and operational. And the fourth metric was implementation, which was composed of footprint, complexity, construction, and water supply buffering. So we looked at how big each alternative would be in terms of space needed at the current facility, complexity, what sort of operator attention was associated with the technologies of each alternative, construction and ease of or lack of with pre-manufactured units, and water supply buffering, how many barriers were between the secondary clarifier at the Moscow facility and the consumer. So moving on to our alternatives discussion, our first direct alternative consisted of ultrafiltration, reverse osmosis, and a UV AOP system. Advantages of this alternative are that each of these technologies are pre-manufactured, so they're compact, highly effective, and relatively low maintenance. The UV AOP system almost instantaneously oxidizes carbon. Concerns we had with this alternative are the reject lagoons that would be needed for the UF and RO systems, as well as the residual hydrogen peroxide produced with the use of the UV AOP system. So in the middle of the slide, you'll see a log removal table for this alternative, which totals to 11.5 across the board. Our second direct alternative was ultrafiltration, pre-ozonation, BAC, and post-ozonation. Advantages of this alternative were that it does effectively remove pharmaceutically active compounds, which are a contaminant of emergent concern and may show up in future permits. This alternative also had the lowest life cycle cost of the three considered. Concerns we had with this were the increased operator attention that would be needed with a biological system, and this alternative also had the largest footprint of the 3 we considered. So for the log removal totals, you'll see 8, 7, and 5.5. So this alternative also struggled to meet regulations. Our third indirect alternative was composed of ultrafiltration, reverse osmosis, chlorine disinfection, and deep well injection. Advantages of this alternative are that the pre-manufactured units are relatively compact, and the addition of an aquifer adds a really nice natural buffer and storage tank for the city. It also increases log removals associated with virus up to 6, assuming that the water is in the aquifer for 6 months. This indirect alternative is also seen a bit more kindly in the public eye, which can be a bit of a struggle with these reuse projects. Concerns we had with this were, again, the reject lagoon that would be needed for those UF and RO systems, as well as any injection well permitting that would need to go through the EPA that might stall progress on this alternative. We also met with the city of Moscow, who would like to move away from the use of chlorine at their facility, so this led us to kind of rethink this alternative. So you'll see the log removal table with 11.5 and 7.5 and 7.5 for totals. because of the city's concerns using chlorine, we decided to replace the chlorine contact chamber with a UV disinfection system. So this makes this alternative even lower maintenance than discussed previously and removes any concerns the city had with that chlorine usage. You'll also notice that log removal values for Giardia and crypto have been increased to 9.5 each. As mentioned previously, we used a decision matrix to make our final design recommendation. And so this was developed using a pairwise comparison system. Across the top, you'll see the metrics we considered, and at the bottom in bold, you'll see the weights assigned to them. So we ranked each of the metrics against one another to develop this pairwise comparison, and we decided to weight treatment the most heavily, whereas water supply buffering we thought was the least important. So this is the final result of our decision matrix. This is a collaborative matrix. Each team member filled one out individually, and then we met to discuss and justify why each score was given to a certain alternative in each metric. So you'll see the weights we assigned to each of them on the left-hand side of the table, as well as the score from 1 to 5, with 5 being the best. That score was then multiplied by the weight assigned to come up with a weighted score for each main metric, which is summed at the bottom of the table. And you'll see that the well injection was the best alternative for what we considered in design. So the indirect category 2 water reuse was our chosen alternative. After the water leaves the secondary clarifier at the Moscow facility, it will enter an ultrafiltration unit followed by a reverse osmosis unit and then being disinfected using a UV system before being injected into the aquifer via a deep well injection.
So in the design portion of this project, once we had selected our preferred alternative, which was the deep well injection alternative, we selected 3 different pre-manufactured technologies to meet each of the treatment goals that we had, and we selected pre-manufactured units due to the ease of installation as well as the simplicity of operation for operators at the facility. And this is the use, what is seen across the industry in projects of this kind of those that currently exist. It is important to note that in our final design, we did not include the management for the waste lagoons that would be needed, nor did we include the hydraulic design for delivering the effluent from the treatment facility to the site of injection. So the first unit that we selected was a WEFTEC VersaFilter ultrafiltration unit. This utilizes hollow fiber membranes of a 0.01 micrometer pore size and is flexible to address depending on your capacity that you see at your plant, as well as having a relatively long runtime between backwashing, which is unique to this unit specifically. The second unit we selected is also a WEFTEC unit. This is the reverse osmosis unit that we selected to be compatible with the ultrafiltration unit that we had already selected. Similarly, this has a relatively large membrane surface area, which allows for a hydraulic capacity up to what we need at the Moscow facility, as well as allowing a little bit of room in case there is hydraulic increases in the future. Lastly, we selected the Trojan UV 3000 package treatment plant for our UV disinfection system. This system has a range of flexibility between how many lamps you put in each module and how many modules you place in each bank, which allows for a more specific hydraulic need to what you see at your treatment facility, as well as allowing for future flexibility if more UV bulbs would need to be added in the future. Lastly, we looked into the regulations and permitting as well as the design for an injection well, which is how our treated effluent would be applied. And this sort of a well would be regulated by the EPA underground injection control policies, would be classified as Class 5, which is a non-hazardous waste stream. We would target to place these wells in Washington State because of those existing potable reuse regulations and projects versus the state of Idaho, which doesn't have anything of that scale currently. We think that the permitting as well as the approvals for a project of this size injecting into the Grand Ronde Aquifer would have a greater success if it were placed in Washington State. So with this, we have two different options between injecting into the upper Grand Ronde Aquifer or the lower Grand Ronde Aquifer. If we choose the upper aquifer, it's less expensive, less drilling, less material required, but there is a greater frequency of wells that draw out of the upper aquifer. Whereas the lower aquifer has less wells that draw out of it, but it would be more expensive to get into that lower aquifer. On this slide, you can see an image that shows where the current wells are drilled into the upper and the lower Grand Ronde Aquifer as of 2012. And so we have two recommendations. The first and the primary recommendation being drilling into the lower Grand Ronde Aquifer if possible and if funding allows, as this would have a greater chance of meeting the 6-month requirement for time between the effluent being applied and being drawn out for a greater length of time versus the second option where we would drill into the upper Grand Ronde Aquifer, and we currently can ensure that we would meet the 6-month travel time in the aquifer, but if there is a usage increase in the future, then that might decrease below what we are designing to right now. Finally, when considering this project, we had some concerns about the space that would need to be taken up at the facility as they don't have excess amounts of space that aren't being used. But we were able to gain some space by removing the current chlorine contact chamber and replacing it with the units that we have selected. So we did draw those to scale as well as develop a construction sequencing recommendation for how to construct these units and keep the plant operational. And we did find that there was excess space for these units by constructing over where the current contact chamber is. So in review, we selected 3 different industry alternatives that are used for potable reuse. 2 were direct potable reuse alternatives, and 1 was an indirect potable reuse. And each alternative was then researched and ultimately evaluated using a decision matrix that was developed using pairwise comparison and input from the city of Moscow. And our final design recommendation includes an ultrafiltration unit, a reverse osmosis unit, followed by UV disinfection, and ultimately being applied by deep well injection. We'd like to thank you for viewing our presentation and thank the industry professionals and professors who helped us in the development of this project.